Hi folks, today I'm going to talk about metric spaces and what is the definition of a metric space and some of the examples that you have encountered in applied mathematics, such as in electrical engineering or physics or those kind of things. Okay, let's start with a definition of some sort of definition of a metric space. Okay, I will start with the metric space. What is the definition? Okay, a metric space is a pair of a set, I'll call it X, and a function on the Cartesian product of set. In other words, X is a set and D is a metric on X, and this D will act as a kind of some sort of a function that will measure the distance between two elements in X. Then this function D has been defined on Cartesian product of X and X such that for all X, Y, and Z which belongs to X, we have the following statements. Okay, then so far a metric space is two things. First of all, it is a set, I will call it X, and there's a function D. I will show it as a kind of black box that for two elements of X, this function will get these two and will spit out the distance of, if I call this x1 and x2, x1 and x2. This is like a black box. Okay, what are these statements that a set and a function should satisfy for us to call it as a metric space? First of all, the first one is the D is real valued, finite, and non-negative. Okay, this statement is simple. It should be real valued, it's not complex, it is finite, it means it cannot be infinity, and it is non-negative, which is positive, or for any X and Y belongs to X, it should be greater than 0. The second one is the dx and y is equal to 0 if and only if X equal to Y. It means that if X is not equal to Y, then what we will have is just the X and Y is greater than 0. It means that for two distinct elements which are not equal to each other, the distance should be strictly positive. The third criteria is just the dx and y is equal to dy and x. This is called the symmetric property of the metric space, or the function, like the meter that you define on a metric space. This is obvious. Let's go to the fourth one, which is called triangular equality. It is the x and y is less than or equal the x and z plus the z and y. This is called triangle inequality. and this one is called symmetry. Okay, the last one is why is it called triangular inequality? Is because assume that you have a triangle. Let me draw it for you. You have something like this is your space, and this is one element. I'll call it X. This is the second element, Y, and this is the third one, which is Z. And if I make a triangle using these 3 points, then I will have this one is less than or equal to, this is 2 and 3, 2 plus 3. By 1 and 2, I mean that this is the length of xy, and similar for the second and third. And it is some sort of like, this is some sort of, from geometry we know that this is valid, and this is similar, this has the same meaning as this like triangular like inequality that we have in geometry. Okay, using this number 4, we can use by induction, we can have the x1 and xn is less than or equal to the x1 and x2 plus the x2 and x3 plus the xn minus 1 xn. You should be careful because all of these elements, x2, x3 up to xn minus 1, should be in the space that we are going to define them, like meter on it. Okay, now I should also mention that for the space x that we have here, it is something like abstract space. But what I mean by abstract space is, for example, the spaces that we usually work with are, for example, R2, R3, or even R. Okay, and we want to define the notion of distance in these spaces. We are going to say that, for example, in R2, this is X and Y. These are 2 points, and we know that these are points. This is a point, and this is the distance between these two. But generally speaking, all the spaces are not that simple, and it could be pretty much complicated. And for example, we can have a space of functions. For example, continuous functions defined on closed interval a and b with the usual plus, like addition and multiplication by scalar. They will define a vector space. I will talk about vector space in future tutorials, but we can have a space. This space is the space of functions. Then this point is not a point, actually, it's a function. And this is again in the function. And we can define a distance between these two functions. Then as you can see, this concept of distance is pretty much like abstract. It is not like the distance between 2 points in R2 or in R3. Okay, let's have some sort of examples of more concrete examples. The first one is a real line. Call it R. And the distance of 2 elements is is x minus y. When you want to check that if it is a metric space or not, then you have to check that if this actually satisfies 1 through 4, which is pretty much easy to do. I will just prove number 1 and 2 and 3, and you can go for the number 4. It is what was the number 1 is the x and y should be greater than or equal to 0. You know that because this is absolute value, we know that this is greater than or equal to 0. And number 1 checked. The x and y should be 0 if and only if x is equal to y. Then if we want to check, we know that if the x and y is equal to 0, that means that x minus 1 is equal to 0, then it means that x is equal to y. And this one is checked. Now we know that if x minus y is equal to, and if, let's go to the other one. If x is equal to y, then what we'll have is just x and y minus y is equal to 0, then the x and y is equal to 0. Then this is also checked. And let's go to this. This is the second one, and let's go to the third one. Was the third one? The x and y should be equal to the y and x, which we have this because we know that x minus y is equal to minus y minus x. We know equal to y minus x. Okay, check. And you can try the last one, which usually is the most difficult one to do. But for this one, it's really simple. I will have a few other examples here, like Euclidean space. Space R2. Which are, this space of R2 is just ordered pairs of real numbers, which are like A and B. A and B belongs to R. And the meter defined on it is just, you know, the distance that you know from geometry is just zeta 1 minus eta 1 to the power of 2 plus zeta 2 minus eta 2 to the power of 2. And we know that x is equal to zeta 1, zeta 2, and y is equal to eta 1, eta 2. Okay, great. You can do the same like argument that I did for the real line for the Euclidean space, and you will see it's pretty much easy to prove that it will create this space with this function on it will define a metric space. Let's you can also extend this Euclidean space R2 to spaces in like more than 2 dimensions, which is R3, or just similar R3. Okay, and also go to like Rn or even Cn. In the Cn, you will have the order pair, like the Cartesian product of the R by R n times, and this one is R by R n times, and this is like C by C by C n times, which is each element has different parts, and each part it belongs to the complex tree. Okay, let's go to more interesting examples. Let's talk about sequence space. The third example, sequence space, L infinity. Okay, we'll see that in this one you will see the general concept of metric space. What is the set that we are going to talk about? As I said, in any metric space, we have a set and we have a function which is going to act on the Cartesian product of that set with itself. Then, the set that we have here, X, is all bounded sequence of complex numbers, which means that is every element of X is a complex sequence. You see here, every element, it is not like a point. Then X, which is the element of the big X, is like zeta 1, zeta 2 in sequence. We call it X briefly as zeta j. And for all j's, we have the absolute value of zeta j is less than or equal to Cx. This is because of the boundless that we define on the set. And this Cx is a real number which may depend on X, on the element, but does not depend on the index j. This is the space that we're going to work with, and we have to define some sort of like metric on it. The metric that I'm going to define is just which is a supremum of the j, and j belongs to n, which is natural numbers. This is the supremum. If you don't know what is supremum, like, forget about it, assume that this is the maximum. But like because you have like infinite set, you cannot talk about a maximum. It is better to talk about supremum, which is the supremum is just the, if you have like millions of maximums, and the smallest one of them, like if you want to define supremum simply, the smallest one of them is called the supremum. The supremum is a kind of like maximum, right? It's the smallest maximum. This is called, then this space that I define, it is called L infinity. That is called the sequence space. It isn't really difficult to prove that this metric, this meter that we have defined on this space is going to satisfy the number 1 and 4. Then it is not really difficult to prove. But I'm not going to prove it here. Maybe in the other tutorials, or maybe I will just put the proof. I will just prove it like in a PDF, not kind of like tutorial. I will put it in a PDF because it is not really difficult to do. And yep. And the last one that I personally really like is just function space. Space, which is the with the notation of C and D. This means this is a continuous, and this is the definition. This is the domain of the definition of the function, which is the closed interval A and B. And the set that we have here, X, is just real valued functions. Independent, I will show the independent variable by t, and t is the independent variable in the function. And the domain of definition of function, it is j is equal to a and b. The metric that I'm going to define is the distance between any two functions in the space is the maximum of the x and t belongs to j. You may ask that why are you using maximum here? Why aren't you using like supremum? Because you know that we know for any continuous function, and this is a closed interval and it's compact. Any continuous function has been defined in a compact set. It will have the maximum and minimum on that interval. The supremum and maximum will be the same. And yeah, that is a really cool space. I would call this a really cool space. A cool space. I really like this space. And we're going to talk about this space more when I want to talk about dynamic spaces, because the spaces is a complete space. And we know we will have like I will show you that the complete spaces are like easier to deal with because they will have better kind of like properties than incomplete spaces. Okay, then let's finish this tutorial here, and the next one I may go to like more deeper kind of like deeper topics, such as like complete spaces, and talk more about like sequence spaces and spaces which are a little bit like more interesting.